So here's sort of our last catch-all environmental screencast. We're going to talk about toxic compounds, and we're going to spend a very short period of time talking about global warming in a very, very simple, easy to understand way. So when we talk about toxicity, we have to sort of talk about different kinds of toxicity. Toxicity being, hey, if you take too much of this stuff, you're going to die. So we sort of break down toxicity into two very broad categories. One is what is known as acute toxicity, which is the rapid and serious response to a high or short-lived dose of toxic chemical. So imagine a nuclear warhead being nearby and you get irradiated with a whole lot of radiation. That'll kill you. Or drinking a gallon of antifreeze. That'll probably kill you too. Or a gallon of gasoline. That'll probably kill you within, a day. Something like that. That's what's known as acute toxicity. And the way that sort of works is sort of interferes with the essential physiological process. This particular poison makes it such that your lungs don't uptake oxygen anymore, or that no carbohydrates are absorbed by your intestines, or your synapses in your brain don't work anymore. All it basically does is it's some toxin that gets in and amongst some very important chemical reaction that keeps you alive, interferes with it, makes it some other reaction, whatever. You take it, in a short period of time, you're dead. That's acute toxicity. And then there's chronic toxicity. Think cancer-causing stuff. Nobody dies from smoking that night, right? If you have a cigarette, you're not going to be dead that night. And if that was the case, then nobody would smoke cigarettes. No, chronic toxicity is sort of the low but prolonged exposure with a lag between exposure and effect. So I have to smoke for a while, a year or 20 or 40, before it'll kill me. And, everything that we say is, this is a cancer-causing blankety-blank, obviously it falls into the same category of, well, it does kill somebody and doesn't kill somebody else. So acute toxicity and chronic toxicity are really difficult to measure. They're difficult to measure for a couple of different reasons. First, let's talk about how we actually measure toxicity, then we'll talk about how crappy it is. So the way we measure toxicity is we give high doses to animals and we kill them, which would then be our measure of acute toxicity. And then we extrapolate to low or chronic doses, because what we really want to know is these chronic doses. I mean, this is where laws are made, it's down here. I mean, it's easy to make, you make a law that says, oh, don't allow anybody in the workplace to be irradiated with this amount because it will kill them before they come to work tomorrow. Obviously, that's sort of a no-brainer. But this is much tougher. You work in a chemical company. Your workers, use this particular chemical. And the fumes, they're around the fumes. So what's a safe level of those fumes such that you can say, oh, you know what? I don't think my employees are going to die in 20 years from cancer by working for me. So these are really hard. I mean, these are numbers that are very, very important in terms of sort of society. You don't want to kill off your employees. You don't want to kill off your customers, whatever. So we need to have these numbers. We need to know what these toxicities are. So the way we do it is we give high doses to animals and essentially kill them. Why do we give high doses? Well, because we don't want to have to sit around and, inject, take your little rat and let him smoke one cigarette every day for 20 years and then see how many of those rats die from lung cancer. We don't have that kind of time. Nobody wants to sit around and wait 15 years to see how long it takes to kill a rat, or if it does kill a rat. So what we do is we give them, enough cigarettes or enough nicotine as if they'd smoke, 20 years worth of cigarettes, and we inject them in 10 minutes with that amount of nicotine and see what happens. And if it kills them, great. Now we know how much it takes to kill them in a rapid, short, intense amount. That's acute toxicity. And then what we do is we sort of use some mathematics to sort of extrapolate down to the lower the chronic doses, because that's the numbers we need, is we need those chronic numbers. And that extrapolation is a purely mathematical extrapolation, and it's kind of tough because every chemical that's sort of nasty, all these toxins have sort of different physiological effects. If, for example, if I drink a gallon of gasoline, it will probably kill me by tomorrow. But if I take that 1 gallon of gasoline and I put 3 drops into every cup of mocha, that I drink every day, and it takes me a year and a half to drink that gallon of gasoline, I'll be perfectly fine. I'll never show any adverse effects because my body is built for processing toxins. Humans have been processing toxins for eons, for hundreds of thousands of years. Humans have been able to consume small amounts of poisons, and their body gets rid of them. That's why we have a liver. We know this because humans, for most of their life, did not wash their food, and we ate dirt. Dirt is loaded with a whole bunch of nasty stuff. And you know what? They didn't die. Our ancestors didn't die from eating dirty leaves or dirty strawberries or raw meat. Because if they didn't survive that, they wouldn't have been around long enough to procreate and wouldn't have had children. The human species would have died off. So obviously we've evolved into an animal that can eat a certain amount of toxins and still survive. So why is this method, this is the only method we got. Kill animals and do some bad math, which isn't very accurate. But we do it anyway because it's all we got. All right, so let's talk a little bit more about why this is crap. The first is the nonlinearity. Every chemical, like I was saying, this extrapolation is a mathematical extrapolation. And it's not linear. And each chemical is a little bit different. I can drink that small amount of gasoline, but mercury, which we're going to talk about in a second, mercury bioaccumulates. So if we figure out, for example, that if I consume 1 cup of mercury liquid, it will kill me tomorrow. If I put a couple of drops of mercury liquid in my mocha every day, eventually when I get up to a cup, I'll be dead. Because humans have not figured out how to flush mercury from our system. So it accumulates. Part of the reason why humans haven't evolved to flush mercury from our system is because for most of our human existence, we weren't exposed to mercury because it's all underground. It wasn't there 200,000 years ago when we were walking around with the dinosaurs. So we don't have any experience with it. A whole bunch of other toxins that are all man-made. We pulled the mercury out of the ground when we started mining for gold and silver a couple thousand years ago. That's when we found out the problem. So mercury bioaccumulates, and so the chronic toxicity is very close to the acute toxicity. Whereas again, antifreeze or gasoline, the acute toxicities and the chronic toxicities are very, very different. If you take it slowly, your body can process the gasoline and flush it out and everything's cool. So the equations to go from, if this is what it takes to kill a rat in a day, this is how much it would take to kill a human over 40 years, that equation is not simple. So that's the first problem. The math is wrong. 2, animals ain't people. Animals are not people. We have completely different physiologies. And so saying, this will kill a rat, but I'm not a rat. I'm a human. And so I have different physiological processes. I have similar physiological processes, but they're still different. The cases of saccharin. Saccharin is a natural sweetener. I'm sorry, not a natural sweetener, an artificial sweetener. You might know it as sweet and low. When saccharin first came on the scene as an artificial sweetener, it's great. You can put it in your coffee and it tastes like sugar and there's no calories. And of course, we're Americans, and so we want our sugary taste without all the calories. So we come up with fake sugar, and saccharin was one of the first ones. Saccharin, or sweet and low, causes cancer in male rats. And for a long time, decades it seems, there's a warning label on every single little packet of saccharin that says, this chemical is known to cause cancer in laboratory animals, which is what the FDA said you had to put on there. But the thing is that it causes cancer in male rats. It's not the saccharin that causes the cancer. It's an enzyme that male rats have. What they do is they basically take the saccharin and turn it into the cancer-causing chemical. Saccharin itself is not the cancer-causing compound. It's what male rats take saccharin and turn it into. They turn it into the cancer-causing agent. It's a certain enzyme that male rats have to make saccharin and turn saccharin into a poison. Well, female rats, they don't have that enzyme. So you can inject all the saccharin you want into a female rat and she'll never get cancer. Male rats, they get cancer. Turns out humans are just like female rats. We don't have that enzyme either. So you can inject all the saccharin you want and consume all the saccharin you want, and you won't get cancer by the same method that the male rats do, which is the warning on the label. It's because the male rats get cancer. You'll never get cancer because you lack that enzyme. So why, you ask yourself, why are the labels on there? Well, the labels are on there for about 15 years because there seems to be a disconnect between the science and the legislation. And this would not be the first time where the politicians don't quite understand the science, but that's a different discussion for a different time. And of course, not only do we have the nonlinearity and animals aren't people, but people are different people. So everybody has different physiology. What's my evidence of that? Well, some of us have a family sort of disposition or a genetic disposition towards high blood pressure, right? If you have parents, aunts, and uncles who all die in their 50s and 60s from heart attacks, chances are you need to watch your salt. The reason you have to watch your salt is because your kidneys don't do their job. Sorry, your parents is, their DNA, just their kidneys are not very efficient. So then flush the excess salt that stays in your system and you end up with heart attacks at 50 and 60. So you have to sort of watch your salt intake. Well, for those of us lucky individuals who have no genetic history of heart problems, that means that our ancestors, our immediate ancestors, parents, grandparents, their kidneys seem to work just fine. So chances are your kidneys work just fine, which means I can put as much salt on my fries as I want. I never have to look at my salt intake because I was blessed with good genes in regards to my kidney being fully functioning and flushing away the excess salt. No problem. I can drink pickle juice while I'm running. No problem. And I do, and it tastes delicious. So again, we make laws for chronic doses of toxicity, and of course they're wrong because they're not linear. They're wrong because they're based on killing animals. They're wrong because we killed them, not looked at the low chronic doses. And they're wrong because everybody is different. But we still have those numbers, and politicians still come up with the numbers. And we'll get the next part in the next screencast.